All right. I want to also tell you all about the next week's panel discussion. So we are ending this series with a very nice panel discussion where we have our speakers come together again for a very nice sit and do conversations via Zoom. And it will be moderated by Sumana and Rishika, who are our own Women Who Code data science leaders. And in our panel, we have Angela, Madhurima, Laura, and Vandana. If you attended our previous webinars, you know all these people, and they're like very much an established data scientist. So they will be in the webinar, sorry, in the panel discussion, talking about various things. So what to expect are career conversations of their careers, how they started and where they are right now, and how and where to get started. So if you're a beginner or if you're trying to get into data science, we will talk about that as well. And then how to transition to data science if you are from other branches, or if you want trying to get into data science. So that's something we have discussions. And then we have a special discussion on mentorship. So this is something that's going to be very interesting because we are trying to see if we can have a mentorship program. So there will be some discussions there. And then we also have a live Q&A to top it off all off. So all this is going to be on March 27th at 12 p.m. ET. So make you guys are present for that. It's going to be very nice, very bubbly conversations between our speakers. And also at the end, we have a free bundle of resources that will help you to kickstart or reinforce your data science journey. And that will be shared at the end of the panel discussion next week. So please watch out for the links to register and the promo for this on all of our social media channels. And before we begin, as usual, putting together this whole massive series was a hard task, and it would not have been possible without our volunteers. So a huge shout out to all of them. And next, I want to give a shout out to our sponsors as well. They have been wonderful support to our community in putting together a lot of virtual events. Yes, so we have so many events because of them. So thank you. And also, if you are new here or if you missed any of our previous webinars, here is the list of link to our previous webinars. So exploratory data analysis is where we started. We have everything, the YouTube videos and the GitHub code and other adjoining resources that you will need. And again, I just want to reinforce that this webinar series is based on statistics in data science. So if you are new or if you want to brush up some more of the knowledge in machine learning, I highly recommend Introduction to the Machine Learning series and Advanced Machine Learning series. So these are two series that were put together last year by Women Who Code itself, and they contain everything that you need to learn about particular models and anything you want in data science. So if you want to get a full picture, I highly recommend going through these series as well. And for today, we have Laura to cover topics like PCA, k-means clustering, hierarchical clustering, model-based clustering, and then other clustering related issues. The best part about this today's topic is we to start with the fundamentals of statistics before diving into this, just to reinforce all the learnings you have had so far in the series. So I'm excited about that. And Laura has put together a very informative and very interactive collab notebook, and I'm sure she has some problems and takeaways at the end of the notebook. So to talk a little bit about Laura, Laura is a data specialist who has previously worked in fintech, advertising, and forensics. And she loves all things data, particularly data cleaning and visualization. So that has been her strong suit. And currently she's launching a tech or a data consultancy called tech by humans, and in that she's spending her time in creating educational content, and it is called Taught by Humans. um, and it is really nice. It's a very good initiative, and please check that out as well. And yeah, so she would be our speaker for today. And before we begin, make sure you click on this link to open the Collab notebook. In the meantime, Shavia would also be sharing this link in the chat for you guys to load the page. Laura, are you here?
Yep, I'm here.
Oh, awesome. Your video is off, so I thought probably you haven't read it.
It says I can't share it.
Oh. Can you do that now? Awesome. I'm so sorry. Anyway, so Laura is our speaker for today, and I hope you have opened the Google Colab notebook. And Laura, you can take it away from here.
Hi everyone, I hope you've got access to the Google Colab notebook. I'm just going to share my screen now so you can follow along with me. The code has already ran, everything has ran, so you should be able to see everything I can see. You don't necessarily need to run the code as we go along, just in case you hit any problems, and there are some extra tasks for you to do after this. But I just wanted to talk you through this. So just a tiny bit of background on me. So I have quite a few years experience working as a data analyst, doing a bunch of different, it's data science, but it wouldn't have been called data science then, things. I also do a bunch of data consultancy work now, which ranges from business the whole way through to machine learning stuff. And I'm also doing a PhD on, at the minute, I'm looking at online attitudes to AI using natural language processing. So statistics and unsupervised learning are a big part of what I do. I actually did a mathematics and statistics degree a long time ago, and I've always thought that statistics and machine learning were the same thing until I started doing some research for this course, for designing the content for this session. And I found it really interesting to split them apart and see them differently. So I'm going to talk you through that as we go. So I think last week, if you were at the session, it was on supervised learning. Supervised learning is when we tend to think of things like neural networks that define images as a cat and a dog, or a financial algorithm that tells you whether or not it's going to give someone credit or how much to lend money to someone. And why that's supervised learning is because the human already splits the data into groups before it starts. So if we had a neural network that we were trying to train on images of cats and dogs, we would give the neural network a bunch of images that we've already said, these are cats and these are dogs. With unsupervised learning, we actually just give the algorithm or the neural network a bunch of data and we say, do something cool with this. So we might give it a bunch of images of lots of different animals and it would split it into groups for us. That's not necessarily a very useful thing. And that's one of the big issues with unsupervised learning, is it's quite difficult to know that you're going to get something interesting out of it. I've used it in work before to do customer segmentations. So say we have a group of customers and we've got loads of data on them and we don't really know what to do with this data. Putting it through the kind of methods I'm going to talk about today can actually end up with really interesting groups of data, groups of customers, sorry. One of the things I worked on was a market research campaign for L'Oreal Cosmetics, and we used one of the methods, K-means clustering, and PCA, to segment different customers for different makeup users for L'Oreal, which I thought was quite a cool use case, and we got really interesting things that we wouldn't have come up with ourselves about how to group the data together. And this is just a bit of a diagram to show you how I think of supervised versus unsupervised learning. I've put in here this really detailed background. If you want to read through that, it just talks about what the differences are, and there's some blog posts that you can read, and I'm not going to go through that today because it's a bit more theoretical. I wanted to get straight into statistics. So whenever I think of machine learning, I always think of statistics because it's based on so many statistical concepts. And what we've got here is we've got the different libraries from Python that I'm going to use to write this, which are NumPy, Pandas, and statistics. I'm sure you've seen those before, and you've probably used them if you've done any of the rest of these courses. I've also got two files. So they're taking, someone made a data set of measurements of oranges, lemons, and apples. So their width, their height, and their weight. And I took that data set and I've just used it for this course. I edited it a little bit, and you can download the files if you click on this link. They're here. And what you need to do is just put them here in the Google Colab if you wanted to follow along. And what we have is a group of fruit and then a group of labels. The labels are just there so we can check how well our unsupervised learning methods work. So reading the data in, just doing a bit of data cleaning at the beginning and looking at the data to see what it looks like. So here we've got the different data sets, and I did a little bit here where I combined them together. I'm sure you've covered this in the other classes, but there's the data combining and cleaning part of any data science is the most important part to make sure you've got good data before you start with. So I went through here and just kind of cleaned things up a little bit before we started. One of the most important concepts that I think exists in statistics is measures of central tendency. And what that's measuring is what is the middle point of the data. And there's three main ones. I'm sure you've heard of them before: the mean, the median, and the mode. So the mean follows this equation. So it adds up all the points and divides them by the number of points. It's whenever we talk about the average, we're normally talking about the mean. So using the statistics package, we can work out the mean for height, but also if we actually use pandas, because we've made fruit data into a data frame, we can actually just use this function mean, and then we get the mean of all of them. So it's not actually very useful for type, it's only useful for the other three, but we can see the mean of all of them. And then if we wanted to call the individual one, which we're going to do later on, we can then use these square brackets and the name of the column. And the median is if you line all the data points up in order, the one that's in the middle. So I always think of this in terms of height. So if you had the height of a bunch of fruit or a bunch of people, you lined them all up. The median is the one in the middle. So if there is an even number, it's literally just this, and then it's slightly different if it's an odd number because you have to add them together. We can access that in exactly the same way. If your data set is normally distributed, which I'm going to come on to later on, the mean and the median should be the same. If it isn't normally distributed, they're not. And then we have the mode, which is the most common value used in a data set. It's mostly useful for discrete data, so numbers that aren't continuous, like shoe size and things like that. And also for nominal data, so categorical data that doesn't have any order, that's when mode is most useful. It's calculated just by using frequency counts, which is just when you count how many of a certain category exists. So for example, if we had a list of category of year of student, or where you're from in the UK. So I'm from the UK, so whether you're from England, Scotland, Wales, or Northern Ireland, and we just counted how many people said they were from each country, then that would be the mode value. Again, we can get it for an individual one using statistics, or I just wanted to show you this. So if we then try to use pandas and we use the mode of the fruit data, we use statistics on the width, it doesn't work. And why it doesn't work is because there's actually two values that have the same, there's two modal values. So that doesn't work for statistics, and that's whenever that package kind of falls over a little bit. However, if we use it using pandas.mode, the pandas function mode, you can see here, there's two values for quite a few of them. So for description, for width, there's two values that are the mode value, and it does just print both of them out for you. So that's quite helpful to know, just in case you might have two most common values. So all of these three things are just a way to tell you what's the middle value of a data set that you have. And then we also have measures of spread, and that is what's the difference and how dispersed is the data. So what's the difference from the smallest to the biggest, how many of the values are around the middle point. And that can be quite interesting as well, because if you had a mean of, say, the height was 7 centimeters and all of the values were between 6.5 and 7.5, you could still have a mean of 7.5, but maybe the smallest value is 1 centimeter and the biggest value is 20, and you could still have the same mean. And actually these measures of spread, so variance and standard deviation and the interquartile range, they actually help you get a better picture of the data. And again, I've got a formula here for how to work out the variance. And we can do it in exactly the same way as before. There's a function in both statistics and on pandas data frames. And the bigger the number, the more spread out the data is. And then we also have standard deviation, and the standard deviation is just the square root of the variance. So now on to normality. Normality is a really big concept in statistics. We talk about it all the time. And we say it's been from a normal or Gaussian distribution, and this is what this distribution looks like. It is the bell curve that we talk about all the time, where most of the values are in the middle and they tail off around the extremes. Why we talk about this so much is because we think that if a sample of the population of anything was big enough, it would actually be normally distributed. So if we want like traffic, number of trees, there's a whole bunch of things in nature that just, they are normally distributed. It's been tested over and over again. And you can see here that in this normal distribution, the mean is actually 0. And because it's so equally spread like that, the variance would be 1. So that's how that works. It's yeah, you see we've got a mean of 0 and a variance of 1. So that's what the normal distribution is. And with statistics, quite a lot of statistical methods are based on the assumption that the underlying data fits into this curve. Yeah, so I tried to take a look at one of our data points. So I plotted the height variable from the smallest value to the tallest value. So whenever I look at this, I think, oh, that could be normally distributed. I'm not sure. It does kind of look like there's not very many tall values, and there's a lot around the middle. And how you can kind of take a really quick look at whether something is normally distributed is to use a histogram. So our mean value, if you scroll back up, is 7.1, I think. Let me just check. Yeah, so we got 7.1 as the mean value. So in our bell curve, we expect most of the values to be around 7.1 and then them to tail off around the ends. What we actually have is most of the values are around 7.1, but then we have this weird peak here around 6. So actually our data for height isn't actually normally distributed. That's to be expected though, because we have a very small number of them. But this is something you should check whenever you're doing certain types of statistics, just to check that you aren't going to end up running the wrong statistical test on your data because you've assumed it's normal and it's not. Then we move on to ways of manipulating the data so that we can use them. We say it's transforming the data. So the main methods are standardization, normalization, and scaling. And scaling is just whenever you change the data by the same amount. So maybe you want to double everything and divide it by 5. Normally we do something, we normally do standardization or normalization. So if we have the data set where we just have the height, the width, and the weight, to normalize it, we want to make sure all of the data has a value between 0 and 1. So for every individual variable, so for height, for weight, and for width, individually, we want to get all of them to be in between 0 and 1. And how we do that is we take the minimum values and the maximum values of each of these variables and we work it out like this. So we take the minimum value away and then we divide by the maximum value minus the minimum value, and that puts everything between 0 and 1. Why we do that depends on the method, but for example, a lot of neural networks like you to feed in normalized data before you actually use them. We're going to be using standardized data, which is forcing the data to have, this is the symbol, it's called mu, for the mean, a mean of 0 and a standard deviation or variance of 1. And how we do that is each of the data points, we take away the mean and we divide by the standard deviation. So for each of the ones within height, we take away the mean value of height, which was 7.1, and we divide by the standard deviation. And you can see here these values aren't between 0 and 1. They're not far off 1 most of the time, and they can also still be negative, but it's just slightly different when you're transforming the data. You get slightly different outputs, but this is some of the things that we have to do before we actually feed any data into an unsupervised learning model, and these are very statistical methods. We're also going to be talking about today something called covariance. So we talked about the variance, so that's how spread out the data points are from the mean. But we also have the covariance, and that would be if you have two different variables or two different data sets, how much do they vary together? It's very closely related to correlation. And it's basically like if I have a variable X, which might be income, and I have a variable Y, which might be age, how much do these two variables change together? Do they change together very strongly? Do they change together completely oppositely? Or is there no pattern around how they change together? Why we're interested in that, you're going to see when we go on to principal component analysis, is because sometimes we feed variables into models that actually are very, very strongly correlated, or they covary quite strongly. And then we're actually feeding in two variables that will explain the same sort of variance, or might be putting the same effect in the model twice. So for example, I worked on a project where we were looking at student attainment levels, so student reading levels in primary school. And there was a lot of different variables to do with household income and whether the child was from a single parent family, what type of, or how educated the parents were. If you think about all those things, they can all be very highly related to income of the household. So you maybe don't need to put all of them into the model. And that's when something like correlations and covariances become very, very useful. Now I've added linear algebra in here. So I did a statistics and applied mathematics degree, and I actually find quite a lot of the time I'm using some concepts that I learned in applied mathematics rather than my statistics modules whenever I do machine learning. And that's because machine learning is strongly related to something called linear algebra. And that's just how we manipulate equations and how we use things like that. One of the big concepts in this is matrices. And if you've done any sort of programming before, a matrix is just like an array, except it has two levels to it. So it has, you can see here, it has x1, x12, all the way down to xmn. And matrices are a really useful way to think about data and for us to use data in equations. And it's also how a lot of computation is done. Luckily, whenever I did my degree, in some of my exams, I had to write these out by hand and do calculations in them by hand under pressure. Nowadays, we can just do them on computers, and Python handles these really well and has a lot of built-in things that we can do with them. Yeah, and I added a note here. This might come up later, but if the n and the m of the matrix are the same, then the matrix is called square. It's a square matrix. Yeah, they're very useful. They also have their own rules for how you multiply and divide them together. But again, we can get away with not knowing that as much these days because we can do it on, we can use packages that already exist. Why this becomes useful for us is covariance, which I just mentioned. We actually display covariance as a matrix. So how X and Y, how they vary with each other. If you think about, if you've ever seen what a correlation matrix looks like, very similar to that. And that's how we do it. And we can just use this built-in NumPy function here called cov to work out the covariance matrix, which is very useful. And the final thing I'm going to talk about in terms of linear algebra and statistics are these things called eigenvalues and eigenvectors. I think these words are very odd, but yeah, I use them a lot in my degree. And they are whenever you want to transform or rotate something. And I have a bit of a demo later to explain what this means. But basically, if we have a matrix X and we want to move it, or we want to turn it around, or we want to do something with it, so say X represents our whole data set, we can use eigenvalues and eigenvectors to explain these transformations, so how we would move it. And this is very useful whenever we talk about principal component analysis, but I will come on to that in a little bit. And yeah, just before we started with the principal component analysis and getting into the unsupervised learning a bit more, I just wanted to plot the data. I always like to plot the data so I can see it. So I've got this plot here, and you can see there are 3 different types of fruit, apples, lemons, and oranges. And you can see the lemons are very different from the rest of them. The oranges range quite a lot, and the apples and the oranges are quite similar. So I actually picked quite a difficult data set for the unsupervised learning algorithms to learn, but I thought I would give it a go. Yeah, and then also because we've got height, width, and weight, I just wanted to see how it would look plotted in 3D, and it's actually not very different. But this is just useful because sometimes you have really complicated data that you want to plot in 3D. And yeah, as well as the 3 main types of fruit, they also have these subcategories. So there's 10 subcategories of different types of apples, different types of oranges, different types of lemons. And you can see here, these again, there's some around the edges that are they're very uniquely grouped together. And then these ones in the middle kind of cluster all over each other. So it might be quite difficult for our algorithms to work those out later on. So as you can see here, I've actually got a data set that has 3 variables in it, and it's already quite complicated to kind of like visualize it. And that is one of the reasons why we use something like principal component analysis. It's called dimensionality reduction, because if you think about it, so this is plotted in 3D now. So this data set has 3 dimensions to it. And normally when we have data sets, they have like loads of variables. So if you think about a financial data set, so a data set on you and how a bank was going to decide whether to give you credit or not, it would have your age, your job, your income, your like any record of transactions in your account, maybe your savings account, anything about you, and it suddenly becomes this massive data set with like hundreds of variables in it. So one of the ways we make that a lot easier for us to use is we use PCA, or principal component analysis. And yeah, this term dimensionality reduction, very common in machine learning. We talk about it a lot because we try to reduce the dimensionality before we feed things into models, basically. Okay, so principal component analysis is a transformation. So you have the variables that you're looking at, and we think about them, but we can move them around to try and get a more interesting, I don't know if interesting is the right word, a more useful way to use the variables without them using the same information over and over again. Yeah, some uses of this. So I've mentioned dimensionality reduction, something we call feature selection. So deciding which of the variables to include, which ones to exclude, how much of which variable do we want to include. We can use it with other machine learning algorithms. So you can perform principal component analysis and then use any of the clustering methods I'm going to discuss later, or use something like linear regression or something like that after you've already done principal component analysis. It also helps with visualization. So you'll see that we can transform data sets with hundreds of variables into data sets with 2 or 3 variables or principal components instead. That's a lot easier to visualize. And this use case that keeps coming up is image compression and reconstruction, which I haven't personally done, but I was reading some blog posts about it. It's very interesting. So we're going to talk about rotation. So there's this link here, if everyone can click on it. I'll post it in the chat as well. And this just actually helps you to visualize principal component analysis. It's one of those things that I learned at university and I could do it on paper and I understood it, but it's very hard to explain to someone. And this just like explains what you do. So we've got the 2D example here. and these are the data points that are plotted. And this is, we say this is like the axis that they're plotted on. So if I now move these around, or you can kind of see, this is the principal components of this data set. And all this is doing is flipping it around. So the data points are still in the same place in relation to each other. And when you move them around, you can see all around here, they kind of just flip this green and red line. So this is the 2D example of it. And down here we have the 3D example of it. So we have 3 axes for 3 3 variables, sorry. And you can kind of play around with it and move it, and you can see how it moves when you're just adjusting it ever so slightly. So that is what we're doing with principal component analysis. We're just trying to put the data on a different axis, on a different rotation, so that we can see it slightly differently. And what you see here is when we move it around, I find this one very slow. It kind of shows you how it's changing, where they're actually placed on the principal component analysis. And then here's a really interesting example of eating in the UK. So it was a data set that had 17 variables in it. How much people consume alcoholic drinks, how much people consume fat and oil, how much people consume sugar. And there's 17 different ones, and there is each of the 4 countries that make up the UK. So England, Northern Ireland, Scotland, and Wales. And it shows you the different responses for each of those countries. And then the principal component takes these and says, okay, so these are the same, these are not the same, this is useful, this isn't useful, and puts them together. It tries to explain as much of the variance in the data, so the variance that we talked about, the spread, the differences. It tries to explain as much of the variance in the data set as possible in one principal component, so in one combination of some of these data points. And you can see here, it made a principal component of these 17 variables, and it's got Wales, England, and Scotland really close together, and Northern Ireland up over here. So I'm actually from Northern Ireland, and I know I live in England, and I couldn't off the top of my head really tell you much difference in the eating patterns between Northern Ireland and England. Stereotypically, Northern Ireland eat a lot of potatoes compared to England. And whenever we look at what we actually saw here, it is actually that Northern Ireland eats a lot more potatoes, fresh potatoes, and they eat way fewer fresh fruit, cheese, fish, and alcohol. And that's actually, so if you look at this yellow thing again, the yellow bars, you can't actually see that like quite simply. You can't see the differences off the top of your head. They're quite subtle. And that's one of the powerful things about PCA, is that the PCA algorithm itself can see these very small differences, can see where, so for example, people who eat a lot of sugar and eat a lot of soft drinks, they might be the same, and processed foods, they might all make up the same bit of information, so they don't need to be re-included. So I thought that was very interesting. What would be helpful is if we just, if you want to spend just like 2 minutes playing around with this page to see if it helps you understand it any better, because it is quite conceptual to understand PCA. So I'm just going to give you 2 minutes just to have a look at this, play around with these diagrams and see if how they move whenever you move them actually starts to make sense to you. So I'll give you 2 minutes to do that, and then we'll continue. Some really good questions coming in on the Q&A. Some of them will be answered by the time I get to the end of the PCA section. So I'll just go through that. We are going to talk a bit more about eigenvalues and eigenvectors because that's how PCA works. Okay, I hope playing around with this applet has helped you understand PCA a little bit better. I'm going to go back to the Google Colab notebook now. So whenever we do PCA, whenever we actually do it step by step, what we do is we standardize the data. So we make the data have a mean of 0 and a variance of 1. We then work out the covariance matrix. So how much does each of the variables co-vary with each other? That's to check that we're not including two variables that explain the same variance. We then compute the eigenvalues and eigenvectors. We then rearrange them in a particular order so that principal component 1, so the first principal component, explains the most variance, and then we decide how many to keep. So these sound very vague, and they are, but I'm going to talk you through them. So to do principal component analysis, I'm using some sklearn packages. One is just standardizer, so that helps standardize the data for us without us writing formulas. And then I've also got PCA. They have a PCA package made for us. So I standardize the data. I've decided to use 3 principal components because that's how many variables that I have, and that is kind of how you're supposed to do PCA. You make the same number of principal components as you have variables to start with. So I transform them. That isn't, oh, here we go. So, and then, so this all does all of those steps for me above. And what happens is I get 3 principal components spat out. The first one explains 75.9% of the variance in the data set. So that's quite a lot of the variance. The second one explains 21.2, and the third one explains 2.9. So that's a lot of variance going on in just the first 2 principal components, and the third one doesn't really include that much. Okay, so now I'm going to go back up to the bit on eigenvalues. Oh, no, we're here. Okay, so I've now talked you through how we have principal components, which are talking about rotating the data, rotating and transforming the data. So what we had was we had a covariance matrix, which is a square matrix. So it had the same number of columns and the same number of rows because it has the data across both ways and it compares how much it varies with each other. And what we have then is we want to, I'm just going to go back here for a second. We want to transform the data from here to here. And how we do that is we have to multiply it by a vector or a matrix. So we have to multiply it by a certain amount to make it rotate. This is very mathematical and it's very theory based, and you can get away with not understanding any of this and still doing principal components. But basically, when we move something around an axis, we multiply it by a matrix that has a value for each of those axes. So in this one, it would be 3 points. And that's our eigenvector. That's what we, that's what we would rotate it by. And in this case, we're rotating each of them by the same amount. And because of that, we have one value, that's how much we move it. And that's how we work out our eigenvalues and eigenvectors. It's how much we're rotating things by. That's probably very complicated and confusing. You honestly don't need to understand all of this mathematical stuff behind it to be able to do PCA. But what we're going to end up with is we have our covariance, and then we have a value that we're going to multiply that by. This here, lambda, is what it's called, and that's our eigenvalue, and we get an eigenvector at the end. And did you do linear regression last week where you ended up with an an equation where you multiply each of the data points by a certain value to include it in the model. And that can be a value, a negative value, a positive value, a large value, or a tiny value. And that's kind of what we end up with for our PCA. So we end up with an equation where we multiply. So each of the eigenvectors, so each of the principal components will contain a certain amount of each of the original variables. So say this one could be something along the lines of 7 times height minus 3 times weight plus 4 times width. And that's how we start to think about it. But what normally happens is some variables are included much more than others. And each of the 3 principal components will be very different in the makeup of what they include based on all of it. And then we have a value of how much we are moving these around and how much this all fits together. And that is the eigenvalue, and that correlates to, so it's a number below 1. And that becomes how much of the variance in the data set is actually explained by that principal component. So that's a lot of mathy talk for something. So how is this actually useful? So when we run the PCA, we will get the same number, because we've told it to, of principal components as we had variables in the original model. And then we have to decide how many of them to keep in our new data set. So there's a few methods for deciding. So we've got 3 here. One that explains 75%, one that explains 21%, and one that explains 2.9%. So how many of these principal components do you think we should keep? It's a number between 1 and 3. It could be all 3 of them. It could be 1, it could be 2. Yep, I've got 2 coming through. Okay, so we got a 2. That's, yeah, I agree with Stacey saying 1 or 2. Yeah, we definitely don't need this third one. Explaining 7 or 97% of the variance in the data set is great. So we can decide whether to keep 1 or 2. Some of the methods for deciding are, you literally just pick an amount before you start doing any of this. So you say you want to keep 80% or 70% of the variance in the model, and then you include however many principal components actually explain that. You decide on a minimum value. So we're only going to keep principal components that explain more than 5%. Or we can use this thing called the elbow method. And what we do with the elbow method is we plot each of the principal components and how much variance they explain. And you can see here at principal component 2, it kind of looks like the bend in the elbow. If the elbow was going, yeah, like from here to 3. And what you do is you cut off at the elbow and you keep all the points from the elbow and forward. And that is actually the most popular method for deciding how many principal components to include. So here we go. Again, I thought I'd just give a recap on the eigenvector and value part of it. So what we've got here, if I actually print out the principal components now that we've decided to keep principal component 2 and principal component 3. So this is principal component 1. Here, the first line of this array, this is principal component 2, and this is the one we've decided we're not going to keep. And how this actually works is principal component 1 is this equation. So you can see it actually, principal component 1 in this case actually adds each of them reasonably equally into the model. Principal component 2, however, actually very negatively penalizes weight and has a lot of the height included. And that's how they've decided these two together actually explain a lot of the data and the variance in the data. But here's one of the big problems with principal components. What does this actually mean? So like, what does this equation mean where I've got a little bit of the width, a little bit of the height, and a little bit of the weight? It doesn't actually mean anything in human terms. So back to the example I said earlier about makeup. It was great. We had all these people, these customer segments made up, but someone who buys mascara sometimes and does this, and we're going to take 0.9% of likes mascara. How do you translate that back to English whenever you're trying to talk about it, or a relatable way to talk about customers? But it is a trade-off that you have to make whenever you have 100 and something variables and you want to make it smaller. So it's just something to be mindful of. Principal components aren't necessarily always something that we can talk about, but they are something that's very useful. So what I've done now is I've decided to keep 2 principal components, and I've transformed my data to sit within these principal components. And then when I plot it, this is what it looks like. Sometimes we like to plot the principal components together. So now you can see that I've plotted these principal components. I'm actually getting a lot more groups than I did before whenever I just plotted the data set together. Whenever I just had width and height and weight plotted, I actually can now kind of see distinctive groups forming. Again, this one could just be one really big group in the middle. Maybe it's a few, but I'm actually it's starting to take more form. There's more clusters, there's more things going on. So often principal components are the first step in what you do before you actually do something else. If you have a nice data set and you don't need to use them, that's great. If you need to use them, you can do them before you actually do something like clustering. Yeah. Does anyone have any questions on that part of it before I go on to clustering?
I want to talk about Richard's question of like, why did you choose 3 for PCA? Is it randomly chosen, or is it because the elbow plot showed 3?
Why did I choose 3 for how many principal components I made?
Yes.
So 3 for the original number of principal components is because there are 3 variables in the data set. And I chose to keep 2 variables or 2 principal components because of the elbow plot. So because of where this bend in the elbow plot is. But also this one is quite an easy one to choose because this is such a small principal component that you're definitely not going to include it. It's definitely not going to be useful. But yeah, normally whenever you do principal component analysis, the number of principal components that you make to start with is the number of variables in the model. So if you had 100 variables in the model, you make 100 principal components, and then you decide which ones to keep after that. Does that answer your question?
I would think so. That was a great explanation. Thank you. And there are 2 more incoming questions if you want to answer. How would you explain a grouping in English when you plot PC1 against PC2? How would you explain a grouping when you plot PC1 against PC2?
So when I'm saying grouping, sorry, I'm thinking this is just me deciding it. It's not anything technical. It's my eyes looking at this and saying, these ones in the corner, they look like they're similar. So because they're similar, I'm going to put them together. And again, here in the other corner, there's 3 that look similar. And then there's a bit around principal component 1 equals 1, and principal component 2 is higher than 0.5. There's a group of about 6 or 7 there. And when I say group, I just mean ones that look similar, and they look similar because they're plotted near each other.
Yes, that explains it. Thank you. Yes, you can continue with it, or if you would like, we could take a short break before you continue.
Cool. I'll do the next bit, and then I'll take a very 2 minutes. Cool. So we've done principal component analysis, and the other big unsupervised learning, I guess, group of algorithms that we like to think about is clustering. Clustering is probably one of the things that got me most interested in data whenever I was doing my degree. I just think it has a lot of really useful use cases, and it was always the one that I thought I would get the most interesting stuff out of. Clustering is literally what I was just talking about, where we look at data points that are similar and we group or cluster them together. So things with similar features. I used to work for an advertising company, and we grouped people together based on their phone usage. So if they went on certain websites, or if they used their phone a lot, we had a group called like tech savvy, and they were people who used the internet a lot, never texted, never called. We also had football fans, so they were people who checked the football scores on their phone quite regularly. It was a lot of stuff like online shoppers, and we grouped them together based on bits of information we had about them. And that was how we did that. That's a type of clustering. But I'm going to talk to you about 3 types of clustering today. K-means clustering is one that I'm quite familiar with. I use quite a lot. But one of the big differences between clustering and classification, which you might have already covered, is that in classification we have the groups defined already. So you might want to classify someone into a group of I'm trying to good spender, bad spender, risk when it comes to a loan as a bank, and if you want to put someone in one of those 3 groups, that's called classification. If you just have a bunch of bank customers and you want to put them into groups but you're not sure what those groups are, that's clustering. So the algorithm itself actually gives us the clusters or the groups. So K-means clustering is when we want to split the data set into K, which we actually have to define, K groups that have similar characteristics. And how we work out that they're similar is we work out the mean value of that group, hence K-means, and we try to work out which of the data points are closest to which mean of which group. And what we'd use is something called the squared Euclidean distance. And here's the equation for it. So if we had 2 data sets, x and y, or 2 variables x and y, and we plotted it like this is the difference between the 2 points. It's just a way of measuring distance. There's lots of different ways to do that. And why we might use K-means clustering is to segment based on behavior, but it's also used in bot detection. So if we know someone's a bot and we know someone else isn't a bot, which one is it most like? Which group does it fall into? And the method that we do is we decide how many clusters we want. So you have to pick a number. We randomly put K points as the clusters. All of the points are assigned, all of the data points are assigned to the closest mean, the randomly assigned mean. And then it's recomputed based on which group is, which data set should be in which group, based on which one is it closest to. And the groups are recomputed again, and it keeps going on and on until the means stop changing, or all the points remain in the same cluster, or sometimes we just have a max number of times we're going to run the algorithm. So I've actually gone through an example using the fruit data. So luckily, again, we have a lot of stuff on the internet that actually runs, or on Python, that will actually run a lot of this for us. So we don't need to go through all of these steps completely. So how this would work is, say these are the data points that we're going to use. It might randomly draw, say we say K equals 3. It might draw one cluster at 3, 1. So here, and it might draw another one here and another one here. What happens then is all of the points are assigned to the group, to one of 3 groups, based on which of those 3 random points they're closest to. Then the center of the group is calculated as the mean, the average in the middle of that group of points. Again, it's recalculated again, which of the points are closest to which of the means, and it keeps going and keeps going and keeps going until they all kind of stay the same, or we've done it too many times. And that's a really useful way to get groups that maybe we didn't see before. And here we have an example again with the fruit data. So I've just taken the height and the width this time. And I've used, again, from sklearn, it actually has a k-means algorithm for us. I decided on 10 clusters because, if you remember, there was 10 types of fruit, so 10 subcategories of fruit, and I just wanted to see how well it did it for them. So I've said I want 10 clusters. I've then fit it to the data. It does it for me. I've said the max number of times I want it to run is 300. So that's the pre-programmed amount within this algorithm, but you can say it differently. I've then given it labels. So it's going to give it labels between 1 and 10 because there's 10 clusters. It's worked out, this is me just saying, can we have the center of each of those clusters? And then this is what I've plotted. So sorry about the colors. I couldn't work out how to get them to be easier to see. So basically we have groups from 0 to 9, and the darkest one in the middle isn't actually a data point. It's the center, the centroid point. So we've got this cluster here, the purple one, which I think is 4, and then we've got one over here, and then it's split the middle in different ways, and it's split them out. So what I did was I actually plotted the original ones with their original data set, and if you look at it, it's actually done quite a good job. Obviously there's a few that are in the wrong ones, but they do overlap quite substantially, and it's done a reasonably good job of plotting labels for each of these. Yeah, so it's got them all over the place, although if you notice, it's got the centroid point for this orange group. It's actually here, if you can see where I'm pointing. It's here, we're between 6, near 6 on the width. So instead of having the centroid point quite near to that one, it's actually worked out way over here. So it's probably got this whole big area here in the cluster. Unnecessary, it's got all the right clusters. And then how this can be used usefully is now if we had another bit of fruit and we measured it, we would add it into this algorithm and it would work out which of the groups it was nearest. And then it would decide which fruit it was based on that. So where the centroid point is actually quite important. Yeah, so you can see it's kind of clustered these and it's quite similar. Ignore the colors and just look at the ones that are similar. It's quite similar to the ones we've got going on down here. Yeah, and this was just me trying to work out a useful way to see if it had the same labels we had that were there originally. So if you look at this one, so we've got labels from 0 to 9 and then from 1 to 10 here, and it's actually cool. So you can see here that label. Oh, sorry, my internet cut out. Can you still hear me? Okay.
Yes, we can.
Cool. Okay. We've got label 0 here, which is the one that was predicted. And we've got label 10 that we had originally. And all of them have, all of this label is actually label 10. But some of these label 10s have actually been classified as a different one. So the algorithm that we trained actually split this group into 2. This one, it did perfectly, group 2. They're all 1. If you see what I'm doing, so this is how I was trying to check if I had done it properly. So for example, group 7 is actually split across four different categories. So it didn't actually do it super well, but it did a good job on some of them. It didn't deal very well with the middle section, which is quite difficult because they kind of all overlap with each other. They're not quite distinct groups. So that was just how I was looking. It's called a crosstab. It's just when you plot 2 things against each other and you tab 2 things against each other in a table so you can kind of look at them. I also then redid it with 3 clusters. So with just trying to get it to do the 3 fruit. So all I changed was here I put n clusters equals 3. Ran the same code again, and we've got this group here at the bottom. Again, the center is quite far away, and then we've got this group over here and this group here in the middle. And yeah, you can see not quite correct because we fed it in quite complicated data, and it's actually put all of these points together in the middle. So unfortunately, while it's a great algorithm, it doesn't work for the type of data we're trying to feed into it. How I think it would work better would be if you fed the weight into it as well. So I left a task for you to do, if you'd like to, after this, which is to try and do this again, but to use the height, the width, and the weight. Or you could feed in the principal components and see if that works out any better. But those are some tasks for you to have a play around with. Sometimes mean doesn't work, and we have the median if it's not very normal, if it's very skewed data, or we have the mode if it's grouped data or something like that. And there are actually algorithms called k-median and k-modal data, which are quite good as well. This k-modal is a little bit complicated, and I've never seen a really good algorithm using that, but that's just in my experience because it's a little bit more complicated. Again, to decide k, so have you noticed we had to pick k? And it's just like we have to pick k. So I've picked two random numbers, 3 and 10, because I knew we had those labels beforehand, but normally you don't really have those labels. So there's different ways you can pick k. Again, we have an elbow method. So this becomes quite ugly math in a Google Colab because of the way they do these summations. But we can use something called the within cluster sum of squared errors. Quite a mouthful to say, but what that does is it works out within each cluster how different is each of the points to the rest of the cluster. So yeah, it's just a way of working out our errors. So we can work this out. I wrote a bit of an algorithm for working this out here, and again we have an elbow. So you can see here, this we would stop at 3. We would say 3 is the ideal number of clusters. So what I did here is I ran k means for every single value between 1 and 21, and I worked out the WSS for each of those. And then I plotted the WSS, and we're trying to minimize it, make it as small as possible. So yeah, we've actually got here 3 is a good one for us to use, which is interesting because we actually have 3 different types of fruit. So you can see it works quite well. And then we also have this other one called the silhouette method, which is a bit more complicated. It works out the similarity between groups, but also the dissimilarity of a point to the rest of the groups. So what I mean by this is it would look at this point here and say, how similar is it to these little points in the same green group as me? How different are we from this blue group over here and this orange, I think that's orange group over here. So it's a bit more complicated. It's probably a bit better. And again, we're trying to maximize it. So it's actually, yeah, it's plotted here and it's a bit all over the place. So it thinks we should have 5 groups. But it's just, you can use either of those. They're just different ways of working out how much K should do without just randomly suggesting it. Another type of clustering that we have is hierarchical clustering. And it's a way of splitting data. You don't have to decide how many groups beforehand. You do have to decide how many groups at some point. We also get a really nice diagram out of it, which is a way some people like to use this. And there's 2 methods of it. I really struggle saying these words: agglomerative clustering and divisive hierarchical clustering. Yeah, so one is bottom up and one is top down. So I've only ever really seen this one used before. And what we say is you have so many data points. They're each in a group by themselves, so they make up their own little cluster. I tried to do an example of this with Pokemon. So each Pokemon was in its own group, but it just got too complicated to move across into Google Colabs. What we do next is we group together 2 of them, and then we were the 2 that are closest together. Then we repeat and we group together the next 2 clusters that are closest together. So that could make 3 together, or it could make 2 2s, and we keep going and we keep going until they're all together. So I made a diagram to explain this for you. So each of these shapes are data points. They all exist in their own cluster. Now these 2 circular ones are actually the closest together, so we group them together. Next, these 2 square-shaped ones are the closest together. I mean, by closest together, I literally mean by physical space. So we group them together, and then we keep going. So next, I would say this one here, the slightly slanted one, is closest to this one. So we'd group those together, and then we'd group these 4 together, and then we'd group these 3 over here together, and then everything would be grouped together. So you can see we've actually got like quite a few clusters going on here. We've got the big grey one, then we've got a yellow one and a green one, a blue one, a pink one, and a purple one. And that is how hierarchical clustering works. We work out how close they are together. We use something called a distance measure. So if you remember for the k-means one, we use the squared Euclidean distance. There was an equation for that. There's different methods we can use. We often use just the Euclidean distance, which would just be the center point to the other center point. There's an algorithm for it. We can also use the minimum one. We can use a lot of different methods. We could also then use a bunch of different methods for how we compare clusters. So is the cluster distance from the other cluster, is it the shortest distance? Is it the furthest away distance? Is it the average distance, or is it from the center to another center? There's no right or wrong way to do this. They're just decisions that have to be made whenever we're doing this type of clustering. In this example, when I was doing it in my head, I was doing single linkage. So I was like, which of these squares is closest to the other square? If I was doing centroid linkage, I'd be looking at the midpoint in between the two squares and how does that get to the middle of this square? It's different use cases require different things. And this is the diagram that we get. It's called a dendrogram. Like I said, a lot of the words in this clustering stuff I find so difficult to say. And how it works is you can see these two were connected with the shortest one, then these two next. And what this measures is both the similarity, but also the dissimilarity between shapes. So you can see here that these two shapes weren't in any clusters together, so they're actually the most different. These two were in a cluster together, and this is the cluster that they're all in together. And the vertical lines represent how, like, the shorter the vertical line, the more similar the shapes were to each other. So these two shapes were the most similar, and so on and so forth. Again, this one I use SciPyLearn, has a hierarchical clustering model, which I quite liked, so I used it. I ran it on our fruit data. I used single method linkage. You can just tell it which method you want to use. And I used the Euclidean distance as well. And you can see this is all of our fruit samples. This is how many groups it puts it into. So there's a lot of groups going on there. It's actually a really ugly diagram, just the way it's been done. But how we would actually decide how many clusters to keep is we set a threshold of the distance between the clusters. So if, for example, we draw across at number 2, at 2 Euclidean distance between them, then we would have 2 big massive clusters. If we made it 1.5, we would have 3 clusters, this one here, and then these ones over here, and so on and so forth. That's how we do it. We normally try to keep one that interacts with the tallest line as well, if possible, because that's actually this group here. It's very dissimilar from everything else, so we quite like to keep it by itself. I've set another task if you would like to do it afterwards, which is just looking at the documentation for hierarchical clustering and changing some of these methods just to see how much it changes and how differently it actually interacts whenever you change some of the methods for hierarchical clustering. And the other method, divisive hierarchical clustering, we do it literally the opposite way around. We put everything in the same group and then we split them off into different groups as we go until every single data point is in its own group. So it's the exact opposite way. And its diagram would just look the other way around from this. So you would start off with all of these together, split them into 2 groups, split them into 3 groups, split them into 4 groups, and so on and so forth. I've actually never used that method ever. Like, I've never had a use case to use it. I've always read about it. I always read about it every time I read about hierarchical clustering, but I've never actually used it. And the final method I'm going to talk about today is model-based clustering. And why model-based clustering is useful is because the previous clustering methods that we've talked about, we don't actually have a model for how the data was gotten. Like I said, the data set we're using, some guy who works, I think, for like Glasgow or Edinburgh Uni measured a bunch of fruit that he had in his house, and we're using that data set. So that actually isn't necessarily a good data set for if I want to know the fruit of or the height of apples all over the world. Whereas if it had been taken as a random sample from supermarkets around the world, we would know that that is a good model. So we don't actually, so we're claiming for the clustering models we've used before that they're definitely, it's going to fit, the next bit of fruit we measure is going to fit into that. It's not necessarily true. And what we didn't see is if there was the same repeated observation or data point over and over and over again, those models kind of break because they can't really deal with it. They can't deal with the same point over and over again, whereas model-based clustering can. But one of the things, so we call this Gaussian, one of them that we use is called Gaussian mixture model. If you remember what Gaussian is, that's our normal distribution that we were talking about earlier, the bell curve. So we are assuming all of the data points come from the bell curve that we were talking about earlier. We are also we're assuming that every data point has a probability of being in a bunch of different clusters, and we're picking one of them. And we also have to know the number of clusters beforehand. So we have to know how many clusters we want to, whereas this one and k-means, we did actually have methods for working out what number of clusters we wanted to use. So this one we can choose based on the threshold. K-means there was ways to run algorithms for the elbow method and things like that. So I picked 3 clusters because that's how many clusters I think need to exist. And what we've done again is we've just split it into 3 clusters. So you see, this is a lot cleaner than before as well. So it's split it into 3 very clear, very succinct, separate, clusters that we've got going on here. So of all of them, to me, that's the most appealing. And again, here we've got 10 clusters, and you can see very logically why these clusters have been selected. They're actually incorrect. It's not as accurate as the rest of them, but they're very neatly drawn. And one of the things you actually get with a GMM or a Gaussian mixture model is you get the probability that every point belongs in each cluster. So you can see here for point 1, they're 100% sure it belongs in that cluster. But further down, we've got ones where maybe that belongs in another cluster. There's like 1% chance, or we've got ones down here that are 21% chance could be in another cluster than we've assigned them to. It's actually really interesting information to get, because it's good. You could have one that's 50-50 and it's been assigned to the wrong cluster, and you can look at that and be like, oh, okay. And what I wanted to say is why I've talked about Gaussian mixture models slightly less than the other ones is, despite the fact I can run a Gaussian mixture model, I do not understand the math behind it at all. I've ran them before. I've never understood the math behind them at all. So I just wanted to say, if the PCA stuff at the beginning went over your head and you didn't understand the eigenvalues, you can use the Python packages out there to run PCA for you. It will someday make sense. It's an easy way to do things these days, is you can run them, you can make them work, and then when you have results, you can look at them and you can say, oh, that's how that works, or you can read up on the documentation. But don't, like, while machine learning is definitely based on statistics, and it's really important to understand the statistics, don't get too bogged down on understanding the statistics if it's going to stop you from actually doing stuff. That can come later on. That's me actually finished. So if you have any more questions or anything, I'd be happy to answer them now.
Awesome. Yes, I do see a question, Laura. It's can you give an example for each of the clustering? Like if, for example, hierarchical clustering, where can you use it versus where you shouldn't?
It's very much dependent on your data. So Gaussian mixture models and hierarchical clustering, I've seen used in natural language processing quite a lot. So at the minute I teach on a text analytics module, and I've seen both of those methods come up as a way to analyze data or group together words. I think the example we used recently was the works of Shakespeare. We were running it through a model like that to try and use it. Hierarchical can definitely be used for customer data and anything that you want to group together. Like I said, I'm not an expert in Gaussian mixed models. Anything that you know is normally distributed and that you know how many clusters that you want, I would say works for Gaussian. Yeah, there's just a few more rules behind it. One of the issues with clustering is you don't know that you're going to get good results before you start. It sometimes takes a bit of tinkering and playing around with, because you don't have predefined groups. You might get groups or clusters out that are gibberish and they don't make any sense to you. And you also might just get an amazing result. It's all to do with the data and how you can feed the data in. I've seen people do the same 3 models for the same data set and get completely different results. So it's just playing around with it and knowing it. There's no hard and fast rules as far as I know.
Right. I agree. With clustering, it every time it can yield different results. Yep. So there are questions on evaluating. How do you know if your PCA performed well, or how do you know if your clustering performed well?
So clustering, if you're doing this for like not proper, if you're doing this, you tend to split things into training and testing data sets. So you would train the model on data that you have. One of the things I guess that it's difficult to struggle with is it's very different training something on data sets that already have labels. So I've used this before where I've extended something that we had labels for. I keep giving the example of customers because it's the one that makes the most sense in my head, but let's say customers or text. You had a lot of text that you were using these models on, and you got some clusters out based on all of the data you had. How you kind of evaluate this is common sense. So you look at it and you say, does this make sense? Does this look so? For part of my PhD at the minute, I'm trying to group together tweets with the word AI or robot in them. And I'm reading through, so I did some modeling recently, clustering, and I read through it, and the groups were all over the place, and they made absolutely no sense. There was no logic why the groups were grouped together. So that's a bad model because I can't make sense of it. I then ran a really, really simple model and got lovely groups out, and it was because I could read words. So I could read ones that were similar and be like, okay, I see why that group has been assigned together. This one I don't agree with, so that's bad. Maybe I'll put that back in and try and retrain it. And it's just things like that. So you have to kind of assess it yourself. Sometimes you're lucky and you already have like a small defined group and you can kind of test against that. Normally with clustering, you just have to check it and sense check it yourself, which is why a lot of people prefer to do supervised learning methods because they're more controlled by a human. Well, they're supervised by a human. That's why you kind of control the results. So I hope that was helpful.
Yes, I agree with you because usually unsupervised learning, it's really hard to get past the business to accepting an unsupervised model versus a supervised model because it's more controlled and it's easy to explain how it works and all that. So yeah, unsupervised learning, it is a bit of a black box, and you always have to know the domain of like, what are you trying to do? Is it doing it, like as you said, spot checking it, and all those come into play apart from other evaluation that you can do with unsupervised learning. Yes. Uh, Thank you for that. That was a good answer. And there is one more question on resources that you would recommend if you have any for learning statistical methods.
I'm a big fan of Kaggle. So Kaggle is, I'm sure it's been mentioned before, it's like an online platform where you can do competitions, but they've really upped their learning recently. And they have a lot of really good notebooks and you can do it all in your browser. You don't need to install things on your computer. It's really, really helpful. It's also, if you have access to courses on Coursera via Work or University, there's some really good courses on there. Actually just being on Twitter and following some good data scientists. They post a lot of stuff. Most of them make resources and blogs all the time. That's kind of what I do. Yeah, just there's courses online, reading blogs. The best way to learn is just to get your hands dirty and just start doing something. So you can read as many blogs as you want to, but just play around with some data, have some fun with it.
Yes, that is a perfect way to learn, I would say. Like how you were saying, like to dive into PCA, you don't have to know about eigenvectors and eigenvalues. Just dive in first, and then the concepts will come together for you eventually as you put it into practice. That is sure. And thank you for that. I just want to point out that if you're looking for resources, we are going to share a good bundle of free resources in our next week's panel discussion, where Laura is one of our panelists, and we'll have a very good discussion on all of the questions you would have next week. So thank you for joining us today. Laura, any closing remarks you would like to make?
No, I would just like to reiterate that don't get lost in the math and being overwhelmed thing. I'm a big believer that you can do a lot of stuff without fully understanding it, and it will. Like, I've done it for years and it's always been fine. So don't get too bogged down in what you don't know. Just start doing it, playing around with it, break things. Error messages are great. They help you learn.
I agree. All right. If you could stop sharing the screen, I would like to make some closing comments, and we will end the presentation here. Awesome. So I hope you guys can see my slides. Awesome. So as I just talked about it earlier, we do have a panel discussion next week where Laura is one of our guests. We also have our previous speakers coming in, Angela, Madhurima, and Vandana, and it will be moderated by Sumana and Rishika. So make sure that you tune in for next week's session. So what to expect in this panel discussion is there's going to be a lot of career conversations. We are going to talk about how to get started with data science, or how to transition into data science, and where to get started. So these are the important questions that we'll be answering. We'll also have some mentorship discussions of how to approach someone for mentorship, why is mentorship important, and how that is going to help you tune your career path. So all that, and we will also have a live Q&A towards the end where you can ask your questions to our speakers. And then towards the end, we also have a big bundle of free resources that will help you with kickstarting your data science journey. So all that is coming up next week. So please make sure you're registered and you're ready to go. And I also want to ask you all to join our Women Who Code Data Science community. We are available through social media and Slack, where we share so many things. So we have a lot of resources that are free for everyone to use, and we are a global community supporting each other to thrive in the tech market. So make sure you join us with Slack. All the webinars, all the resources are available in Slack for you if you're interested in going over them again. And lastly, I do want to thank you all for your feedback. We have been listening to it, and we have been tuning our webinars to accommodate all the requests that come in. So please do take a minute to answer our surveys at the end of this webinar. And thank you all. I hope you are having a wonderful day and have a happy weekend, and we will see you all next week. Thank you.